to have here Andrey Smirnov from the University of North Carolina, and he will give a lecture mini-series on Frobenius structures for differential and Q-difference equations. Andrey, please.
Yeah, thank you very much for the invitation. Let's see how much we're gonna cover today and maybe tomorrow and after that. So I'm gonna talk about something related to arithmetics, and I'm not really an expert in this topic, but hopefully the connection of this story with enumerative geometry and quantum cohomology and K-theory might be interesting. Anyway, so I'll start with a small motivation. So motivation will be some kind of finite sums which appear in number theory. Then I'll try to explain how these finite sums related to differential equations, namely differential equations which appear geometrically as a quantum differential equations for some varieties. And then we'll discuss Frobenius structures for these equations, and I also explain some interesting new formulas for these Frobenius structures and Frobenius intertwiners. And then I'm not sure I'm going to finish it today, but maybe at the end of it, we also discuss some kind of arithmetic analog of a mirror symmetry. All right, and yeah, so since I have 3 lectures and I don't have that much to say, please stop me at any moment, and I can go slow. Well, all right. So let's start from the motivation. So I want to consider this funny sum, which appears in number theory, and it's somewhat an important object. So it's called a Kloosterman sum, or maybe hyper-Kloosterman sum. So it looks as follows. So you take a root, pth root of unity. It may be p-adic pth root of unity or complex root of unity, doesn't really matter. So actually I need to change here something already. So there is no such root in QP, but in some extension of it there is. Well, anyway, so you fix this pth root of unity, and then you consider a finite sum over n variables, which take value in a finite field. And so you raise this this element epsilon to this power. And now you think about x's and z's as elements which taking value in the finite field, about which I think like numbers from 0 to n-1, so it makes sense to raise to this power. You can also look at this sum not over fp, but over fq. So q is any power of p. But then in addition, you're going to put here a trace, which is a map from fq to fp. Right. So that is this simple object. So it's a finite sum of roots. And this object appeared in many different contexts, and many people, many bright mathematicians, considered that sum. And so what we know about it is like one thing is that the absolute value of this Kloosterman sum is bounded, and there is some kind of bound. That is probably the most interesting part of it. So this bound is equivalent, and sometimes it's called as a finite version of Riemann hypothesis. So maybe I'll explain a little bit later that there is some kind of zeta functions behind these Kloosterman sums. So you can organize them into one zeta function, and then the properties of zeta functions, like Riemann hypothesis and so on, should follow from bounds like this. So we also know that this sum has the following structure. So there exist some algebraic integers, so roots of some polynomial equation with integral coefficients, such that Kloosterman sum associated with this field Q given by p to the power s S.
Probably just a second. For our
Uh-huh.
students, the trace from FQ to FP. So just
Yeah,
regard every element on as a multiplication, which can be regarded as a linear transformation over the field FP. And then you pick
exactly.
the
Yes.
trace. Okay, yeah,
Exactly.
thank you.
Exactly.
Another question for students, you didn't put absolute value in the left-hand side of your zero
Oh,
state.
okay. Like this.
Yeah.
Yeah, thank you. Yes, and so there are some algebraic integers. So s power, so to say, of this Kloosterman sum is given by sum of s powers of this algebraic integers. So it looks like a trace of some matrix of some of some power of a matrix where alphas appear as eigenvalues of this matrix, and again, in like a bit later, that the matrix is going to be a Frobenius structure for the corresponding quantum differential equation. And so what we also know is that if we consider the sum p-adically, so these alphas can be considered as element in the p-adic field, then we also have that their valuations are given by, so the valuation of alpha I, p-adic valuation is given by I. So it's more or less, it should remind you the degrees of cohomologies of Pn. So behind that story, there is quantum differential equation for this variety, and valuations of these eigenvalues are related to degrees. All right. So we have this sum, and this sum is an analog of a well-known integral, which appear in quantum cohomology, namely the mirror integral for projective space. So it's my next slide. So I'm going to recall this story. So if you consider a variety, projective space, and consider its quantum cohomology, so quantum cohomology is a connection on second cohomology of X, which in this case is just C, maybe this coordinate, which I denote by Z. And it's a connection in the trivial vector bundle with a fiber given by Hall cohomology. And explicitly, this connection is given by this formula. So it's a differential plus connection matrix. And the connection matrix is given by quantum multiplication by element in the second cohomology, so by the hyperplane plus. So very, very explicitly, this quantum connection in this particular case looks like this. And when we study quantum cohomology, we are interested in flat sections of this connection. And if you want to compute the flat section of this connection, it boils down to solving the following differential equation. So there is some power series, which I call I. It's a power series in Z. And this power series is annihilated by some differential operator of order n. So this differential operator is written here. And this is so-called generalized Bessel equation. So for n is equal to 2, this is just a Bessel equation. And for higher n, it's generalizations. Right. And informally speaking, mirror symmetry is a statement that this differential equation can be solved, and all solutions to this differential equation, like linearly independent solutions, all come as integrals of this type. So here you see exactly the same function as appeared in the Kloosterman sums, which we discussed. So it's exactly the same superpotential. And different solutions appear as integration of this form over different cycles in the so-called mirror variety. And in this case, mirror variety is just a torus.
Maybe for the students, you will say what's the relation of this quantum differential equation with Gromov-Witten invariance on the project.
So this thing is a power series which can be written as some coefficient Cn z to the power n is from 0 to infinity. Well, and these coefficients which appear here, well, they're rational numbers, but you can think about them as numbers which compute the number of curves of degree n in so Cn is curves of degree n in projective space. I mean, it's not exactly like this because it's rational numbers, but like to say it more precisely, it's certain integrals over moduli space of curves in projective space P and so on. Right. So coefficients of this power series, this is called J function, and coefficients of this power series are related to Gromov-Witten invariance, 1-point Gromov-Witten invariance of this variety. Okay. All right. So this is the analogy which I wanted to emphasize, that this integral is analogous to this Kloosterman sum which appear in number theory. And then the point is that this connection really extends to more or less any other example. So, for instance, instead of projective space, we can study quantum cohomology of Nakajima varieties. Well, it's something slightly more technical, but this is kind of a laboratory in which I doing my experiments. So, for instance, the simplest Nakajima variety is the cotangent space, is the cotangent bundle over projective space. And quantum cohomology of these varieties are closely related to representation theory of quantum groups and so on. And well, the whole story extends. There exists some quantum differential equation, there exists some quantum connection, and we know how to write integral solutions for these quantum differential equations. So, for example, in this case, if you study cotangent bundle over projective space, and you have to study this story equivariantly. So in this case, we need to study equivariant cohomology. So which means that there is an extra action of a torus on this space, and this torus acts by scaling cotangent fibers with some equivariant parameter, which I denote by h bar here. So,
otherwise, Gromov-Witten invariants do not make sense. It's non-compact.
Exactly, yes. So since this space is non-compact, these Gromov-Witten invariants, they are not defined unless you study them equivariantly, so that the set of fixed points, which is in this case is just P, projective space, is compact. But well, and this is a well-known story in this case, and more generally for Nakajima varieties, there exists a similar story, and we can write for this large class of examples, we can write some integral solutions for the quantum differential equations. In this particular case, this solution looks like this. So, since I already mentioned that this whole story is related to representation theory of quantum groups, this is something like a Knyzhnik-Zamolodchikov equation for SL2 hat. So quantum differential equation in this case can be identified with KZ equations. And for KZ equations, again, there are well-known integral solutions.
It's integral over what? Your gamma is...
Right. Yeah. So in this case, we integrating again over C over torus, over C star to the power n minus 1. But more precisely, so if you look at say c to the power n minus 1 with coordinates x1 to xn minus 1, you need to remove hyperplanes like where x1 is equal to x2, x2 is equal to x3, and so on. So exactly where this term vanishing, you remove these hyperplanes, and the result is isomorphic to a torus.
And your form is what? It's a standard form.
Yeah, it's like
volume
it's
form.
a standard volume form. It's like dx over x.
Yeah.
Yeah, and again, there exists some well-known analog of this sum in arithmetic. So, but instead of additive character as before, you have to take multiplicative character. But the idea is the following: if you specialize your equivalent parameter to some rational value, and moreover, let's say that this rational number times p minus 1, where p is some prime number, is an integral, right? So this multiplication cancel out denominator of each bar. Then you can define the following thing. So again, it's an integration, or it's a sum in this case over the torus of the same master function as here. So I denoted by phi this object, raised to the power p minus 1 each bar. And chi denotes a multiplicative character. So it's a character from a multiplicative group of a finite field to p-adic field. So very explicitly, it's actually given by Teichmüller representative. So if you take an element, there is a well-defined element which corresponds to it here. It's called Teichmüller representative. But in any way, this is
in your phi xz, does that include the power h in each factor in the top of the slide?
Yeah. So it's this power is here, right?
And in the definition of a phi, because this is a chi applied to the phi xz.
Oh, okay. I see what you mean. No. It's yeah. So maybe I'm gonna denote phi here, like this product without h bars.
Yeah,
and
that's
then,
what I was
and
thinking.
Yeah. Yeah, but it's like more or less analog of this power of h bar.
Yes.
Right, and so all these properties which I mentioned before for the Kloosterman sum, it's also true here that there is some bound for the value of the sum. And let me go back a little bit. So again, there are some integers, algebraic integers, so that this sum is given by a sum of their powers, and so on. And so these algebraic integers again satisfy the same valuation properties. So it's more or less the same story. And and in addition, in this case, these sums are closely related to Hasse-Weil zeta functions. For instance, one can show that this sum is actually an integer, and so this integer, what it computes, well, this sum is given by the number of points on some hypersurface up to a constant. Well, this constant, I believe, is something like power of p, so it's like p to the power s or something like this. I don't remember. It's p to the s maybe. And this hypersurface is given by this equation. And yeah, what is a and b here? As I said, h is if I assume that h is a rational number with numerator a and denominator b, then to that you can associate this hypersurface. You can consider this hypersurface over finite fields. Well, you have well-defined number of points on that, and well, this is exactly what. And again, this hypersurface should remind you this master functions I mentioned before. All right. Yeah, and this is how this sums also related to Hasse-Weil zeta functions. They compute number of points on hypersurfaces. All right. So let me switch to Frobenius structures for differential equations. So I want to introduce one simple notion, which I need to define the Frobenius structure. And this notion is the following. So let's start with a rational function with rational coefficients. Well, numerator of this function is given by some polynomial in Z with rational coefficients, and the same for denominator. And then we can define so-called p-adic Gauss norm on such functions by the following formula. So it's a maximum of p-adic valuation of all coefficients appearing in numerator divided by the maximum of p-adic valuation of all elements appearing in denominator. And then we can consider the following ring, which is the completion of rational functions with respect to this Gauss norm. So, well, by definition, elements here, they can be given by infinite sums of rational functions such that their p-adic norm, so Gauss p-adic norm, is getting smaller and smaller and smaller, right? So it's some sums of rational functions which converge in this norm. So, for example, this is like a typical example in this story. Well, let's fix some rational number. Well, let's assume in addition that this rational number is p-adic integer, so which means that we don't have any powers of p appearing in denominator of this rational number, and consider the following function. Very explicit. So this function is a power series in Z, and this function by itself is not a rational function, of course, because h here is a rational number. Right? So it's involves some roots. But I claim that this function actually belongs to this completion. And the way you see it is the following, right? So you start with this function and you use very simple algebra to write it in this form. And then you note that, well, this polynomial appearing here as a numerator of this fraction, well, it's proportional to p. So this difference is equal to some polynomial in Z times prime number p. And if you know that, you can expand this whole power, using Newton binomial into power series, and you have this sum, from which it's clear that it's indeed an element in the completion, because, well, this is explicitly an infinite sum of rational functions in Z, and the p-adic norm, because of this extra power of p here, the p-adic norm of each term in this sum is getting smaller and smaller and smaller, so it converges in the p-adic norm. And so we see that it's actually an element in this completion. And this is a typical example which also shows how you can characterize functions like that. So typical elements in this completion, they look like this. So it's a power series in p to the power, which involves this term, p to the power m times some rational function. And so you can also note that there's a very convenient way to characterize elements like this as follows. So if you take this power series in Z, you can reduce the coefficient of this power series modulo p to the power s. S is any natural number. And the answer is a rational function, right? So it's very visible from this sum here. So if you reduce it modulo p to the power s, then it's not going to be infinite sum. It's going to be a sum from m running from 0 to s, right? And then all s minus 1. then all higher terms will disappear, and you get some rational function.
Andrey, is there any specifics to the choice of rational numbers here? If you start with any non-Archimedean field and just do the same thing, maybe it's not okay for arithmetic, but kind of a formal construction.
Well, yeah, in a sense, I believe so. When I'm gonna talk about Q deformations, there is a very similar story, which involves, similar norms which are not p-adic in the origin. But yeah, I guess it's possible.
Okay.
So with the yes question, so basically, at least one can replace ZP by any algebraic integers for finite extensions of field of rational numbers. One fits the prime.
You mean you can replace this thing with?
Yeah. Yeah, by computation by some at some prime of algebraic integers.
Yeah, I guess so. Yeah. I guess so. I never considered those examples, but I don't see why it's not possible. Yeah.
And the EP here, is that a transcendental extension of QP or?
You can in this particular example, you don't really need any extensions, right? So it's just QP. Since, but in principle, you can consider extensions of finite of QP, and add elements with like fractional norms, for example.
Okay, thank you.
Okay. Yeah, and so this is so let me just reiterate a little bit. This is a very convenient way, at least in my view, to characterize elements in this extension. So, for example, if you have a finite field, if you have a power series in Z, and you're wondering, is it true that this power series represents some element from this completion? And the way to do it, for example, using a computer, well, you reduce on the computer all coefficients of this power series modulo p to the power s, and ask, is it true that this power series is now an expansion, Taylor series expansion of some rational function? And this is if this is true for any s, then yeah, you get some element from this completion. And in practice, sometimes it's convenient. I'll explain some kind of experiment, numerical experiment, which involves this computation in a second. Well, okay, now what is the Frobenius structure? I guess my slide's getting smaller and smaller, sorry. So let's assume that you have a quantum connection for some variety x. This is quantum connection in variables z, which may depend on certain extra parameters. So this extra parameters, you may think about them as equivariant parameters. For example, when you study quantum cohomology equivariantly, right? And but in this case, you need to assume that these parameters, they take some p-adic values. And so by definition, Frobenius intertwiner is this E-valued isomorphism, which sends connection at z to the power p. So when you replace variable z to its pth power, with original connection at z, with maybe some other choice of equivariant parameters. If A prime and A coincide, so if you don't need to change the parameters, then Frobenius intertwiner is called Frobenius automorphism. So more precisely, like in details, how it looks. Well, in practice, it works as follows. So suppose you have this quantum connection given to you very explicitly. And suppose you have a fundamental solution of this quantum differential equation. So by fundamental solution, I mean a fundamental solution matrix which is annihilated by this quantum connection. Okay, so I already wrote it here. And then by definition, the Frobenius intertwiner explicitly is given by a certain matrix, which I denote UZ, and this is like a gauge transformation matrix, such that it sends the fundamental solution matrix at Z to the power P to the fundamental solution matrix at Z up to maybe up to multiplication from the right by some constant matrix. Again, you can ask why this constant matrix is appearing here. It's because fundamental solution matrix is defined up to a choice of a basis in your space. So you can know that if you have a fundamental solution, maybe psi, like this, here, and if you multiply it by some constant matrix, maybe here, from the right, of course, this is still a solution of the differential equation. So it's just give you other fundamental solution matrix. And so this equation says that, well, this gauge transformation identifies fundamental solution matrices up to a possible change of basis in your space. Right, and this is some constant p-adically valued matrix. And again, the most important property, the most important requirement maybe for this matrix is that it's not just a matrix, it's a matrix whose matrix elements are in this completion. So this is what you require. This is quite a strong property. All right. So, well, I gave you a definition of this Frobenius intertwiner, but you can ask, how would you compute a Frobenius intertwiner by hand? For example, starting from some experiment, maybe you want to consider quantum cohomology of like projective space and compute by hands the Frobenius transformation matrix. Well, you can do it as follows. Well, you can look at this at your differential equation and compute fundamental solution matrix, say in power series, right? So you just look at this equation. You say that, okay, maybe psi is a power series in Z with some unknown coefficients, and then from the algebra you determine coefficients, say using a computer. I did a lot of experiments like this. And then, well, if Frobenius intertwiner exists, then by definition, again, if you look at this formula here, you can just solve for Frobenius intertwiner. If you do that, you'll find that the Frobenius intertwiner is given by this power series. Again, fundamental solution matrix. Psi is a power series in Z, so this whole thing is also a power series in Z. So I don't need this prime here. And lambda here is some unknown matrix, which is constant. And now you ask the following thing. Is it true that modulo p to the power m, this power series, the coefficients of this power series actually, not the matrix elements of this guy are rational functions for any integer m, 0, 1, 2, and so on. And there is some miracle happening here, which is the following. So again, you assume that your lambda, this constant matrix here, is some p-adic integer, is some p-adic constant. So matrix elements of this matrix, they look like power series in P with coefficients which can take only finitely many values from 0 to p minus 1. So they live in this finite field. And then you can ask, can I find some constant matrix lambda such that this property, this rationality, is satisfied. And in practice, it works as follows. Suppose you want to check this rationality modulo p to the power 1. Well, then all the higher coefficients which appear here in this constant matrix, they modulo p, they don't play a role. And you only have finitely many choices for these coefficients for the zero term here. And then just using a computer, you can try all those finitely many choices and check this rationality property. And the miracle is that in all the cases I know, you will always find exactly one value for this matrix element. Then you do the same experiment modulo p squared. So now you have finitely many choices for lambda 1. Again, you check this rationality using a computer. You ask computer to check all possible finitely many values for these guys. And again, exactly for one value, you will find that your matrix is rational. And so this rationality property completely fixes. There is actually unique constant matrix which is fixed by this rationality property, and this gives you Frobenius intertwiner. And so one of the problem which was interesting to me, like in this experiment, in this computer experiment, you'll find a lot of interesting power series in P, so p-adic numbers, but you can ask what this matrix actually is. And it turns out there is a very interesting geometric answer for this constant matrix. And so this is a result which I wanted to discuss today. So actually is the following: if nabla is a quantum connection associated with some variety x, so here I want to be ambiguous, so I don't want to say what this x is. It may be Nakajima variety, but I believe this statement is more general. And so you can study this quantum connection equivariantly or non-equivariantly. In equivariant case, you have these parameters, and you should assume that they are p-adic integers. And then you'll find that there exists a unique Frobenius intertwiner which sends parameters, equivariant parameters, to their p multiples. So they got multiplied by p. And the constant term of the Frobenius intertwiner, so this constant matrix lambda, is given quite explicitly as an operator of multiplication in cohomology by certain cohomology class. And this cohomology class looks like a p-adic gamma function of the tangent space. So this is so-called Morita gamma function. Well, let me explain the notation here and how is this class defined. But again, for me, it was kind of interesting that I did a lot of these computer experiments. I found a lot of examples of these p-adic expansions. And then this formula gives you a very general answer, which works in all the cases. So how is this cohomology class defined? Well, it is known that this Morita gamma function. So maybe I should give you a definition of this Morita gamma function. It's defined on integers by the formula. So it's a product over all I is running from 1 to n, such that p doesn't divide I. So it's a Morita gamma function with index p. So p doesn't divide I. And then you multiply this whole thing, I guess, by -1 to the power n. So that gives you a definition of Morita gamma function on integers, and then integers, they are dense in ZP. And so this definition extends to all p-adic integers.
So in this kind of, there is nothing integer a priori in this quantum differential equation. So, and for some strange reason, your p has to be prime number in order to this intertwiner to exist. If I take it's non-prime, so what happened?
That's a good question. So, well, since this is a p-adic story, right? So p in this story, p must be a prime, but there is some parallel story which is again involves Q deformation, and in that story, p doesn't have to be a prime number. But maybe I'll discuss more when we get to this Q story.
Yeah. Okay. All right.
Yeah, so this story will be closely related to solutions of Q differential equations when Q is a unit root, pth unit root, but in that Q story, it doesn't matter if P is prime or not. But here, since all these things only defined p-adically, we must assume it. All right. Okay, so how is this cohomology class defined? Well, again, from p-adic calculus, we know that Morita gamma function comes with the following Taylor series expansion. So the coefficients of this expansion, they're called p-adic zeta values. Well, there is an analog of p-adic zeta function, and these coefficients are exactly those values. And then we can use this Taylor series expansion to define this class as follows. So I can assume that X is just the Chern root of the bundle, of the tangent bundle I need. Well, more generally, if you have a vector bundle over X, and X1 to X rank V is denote the Chern roots of this vector bundle. So the first Chern class is just the sum of Chern roots. Then you can define M's Chern class by this Newton sum of M powers. And then you simply define the logarithm of gamma function of this vector bundle V. This using the same formula as its Taylor series expansion, but x to the power m is now substituted by Chern characters of your bundle. And this gives you now gamma class of any tangent of any bundle is just defined as exponent of this sum. So again, this exponent in general is well defined because this multiplication by this Chern classes, it's nilpotent thing, so everything is well defined here. And in particular, I can define it for the tangent space, and that's going to give you some cohomology class, and coefficients of this cohomology class are exactly those p-adic numbers I mentioned. So for example, let's do this example related to quantum cohomology for projective space. Well, let's do things non-equivariantly. So cohomology of this projective space is generated by hyperplane class is one relation. Right? So this hyperplane class is a Chern class, first Chern class of the tautological bundle V. And now, if you want to compute its p-adic gamma class, well, what you do, you know that the tangent space plus the tautological bundle is a trivial bundle over projective space. So in particular, that implies that
the definition of this p-adic gamma function, or that your summation is taken with angles like zeta function, angle summation, you go previous slide. Yes, here. The summation is ongoing from, but you're replacing the x to the nth power by.
Yeah, so here.
By this. X. Yeah, you replace that one in the next by the Chern character
Oh,
CN,
okay. Okay. So
CHN. So should that be CHN?
CHN, exactly. Yeah.
Yeah,
So
okay, yeah, that makes sense.
it was a misprint. Thank you.
Yeah.
Yeah. All right. I guess there are too many N's, right? in PN and N, but anyway, so it's clear what I mean. Yeah. So now this computation implies that Chern character of the tangent space is just -1 hyperplane class to the power m. And so logarithm of p-adic gamma class of the tangent space in this case just is equal to the sum, right? So the sum is running only from 1 to n because higher powers of n vanish. So in this case, it's just finite sum. And the coefficients in this finite sum are given by these p-adic zeta functions. So if you ask how the multiplication by this cohomology class looks like, well, you choose some basis in cohomology. Well, for example, you can choose a basis consisting of powers of hyperplane class. And then, of course, multiplication by this sum in this basis, well, it looks as this triangular matrix, nilpotent one. And on diagonal, I have zeros, and below diagonal, I have these diagonals given by mu1, mu2, mu3, and so on. And again, mu is just the value of zeta function. Okay, and this matrix lambda, which is uniquely defined from experiment, on a computer by this rationality condition, is exactly recovers this lambda. So this is exponent of this matrix here. So you can compare p-adic expansions which you find experimentally with p-adic expansion of these zeta values, and they just coincide. Right?
And what is the size of this dimension of this matrix?
Oh, this is just the size of cohomology of your space. So it's acting. So it acts on H PM, right? And so if you choose,
So that will be the total dimension of the cohomology.
Mm-hmm. Yeah, total dimension of cohomology. That's right. Yes. Mm-hmm. Yeah, and a few remarks. There are some integrality property in quantum differential equations, and there is this certain how it's called gamma conjecture and gamma class introduced by Iritani in the context of quantum cohomology. So what's constructed here is exactly this class with the usual gamma function replaced by p-adic gamma function. So you can say that it's a p-adic version of Iritani class, of gamma class. Now, some remarks. So historically, different quantum differential equations for Pn were considered by Dwork and Sperber. So they don't call them quantum differential equations, they just consider Bessel equations. And they invented the Frobenius structures for those equations around 70. So they proved these Frobenius structures exist, and they even wrote formulas for these matrices, but not in this.
Why they needed Frobenius structures? What purpose?
Oh, yeah. So in a second, I explain how these Frobenius intertwiners are related to Kloosterman sums, and they proved some these bounds for the Kloosterman sums I mentioned using p-adic analysis, and they studied for these Bessel equations, and then from that they derived some bounds on the Kloosterman sums. Okay. And an interesting thing is that they gave some formulas, like for example, Dwork himself, he considered only the case n is equal to 1. And in this case, this matrix looks like 1, 1, and then some gamma, and gamma is some p-adic integer. And Dwork gave a combinatorial formula, which for the p-adic expansion. So gamma looks like ci p to the power I. He gave some recurrence relation which computes these coefficients. But the interesting thing is that he never mentioned p-adic gamma functions in this context. I'm not sure why. Maybe p-adic functions just appeared later. Yeah. So and the same is the same comment goes to higher n. So it was generalized by Sperber. And then for T star PNs, this result is in a sense is also known because quantum differential equations describing these cases are hypergeometric equations. And there is a well-developed p-adic story for hypergeometric equations. So it's like people like Kidlaya and who proved that for hypergeometric equations and hypergeometric functions over p-adic fields, Frobenius intertwiners exist. But what I can prove is that this whole story extends to at least Nakajima varieties, and this includes much more interesting examples which are not hypergeometric, like T-star Grassmannians, T-star like a tangent bundle over log varieties, Hilbert scheme of points, instanton moduli spaces, and so on and so on. So there are a lot of examples of Nakajima varieties. And this very formula, this formula is a universal, so it works for every x. All right. And also one last comment is that there is some story story about quantum differential equations for Calabi-Yau threefolds. And people also studied Frobenius structures in this context. And they discovered that Frobenius structures which are appearing there, they also involve constant term, which is a multiple of p-adic value of zeta function, zeta3. And well, the reason only zeta3 appear in this context is because they study threefolds, and so naturally the dimension of total dimension of cohomology is bounded by 3. And so if you kind of look at this formula, they only see these numbers up to mu3 and don't see it above it. But again, this story is also somehow covered by this gamma formula, and somewhat more general than this. All right, so maybe the last few things for today is the following. So now we have this Frobenius intertwiner, which is a map which sends connection at z to connection at z to the power p, and explicitly this gives you some operator which acts on the cohomology of your space. And now, if you specialize these Frobenius intertwiners to points where z to the power p is equal to z, then it actually maps one space to itself, right? So it's not mapping z to the power p, but it just becomes endomorphism of the space of solutions. And so, for example, the trace of this matrix is well defined. So now we can study traces or determinants, like characteristic polynomials of these matrices. So maybe trace of uz is well defined, and it's going to give you some invariant of your equation, right? And so p-adically, we can do the following. We can take any element z, say any element of a finite field, and then lift it using Teichmuller lift to a p-adic number. So I denote by this bracket Teichmuller lift of an element. It's a unique element which satisfies this property. Z to the power q is equal to z. So q here is p to the power s. Maybe I should write it. And then this is the result I mentioned, which relates Frobenius intertwiners for Pn with Kloosterman sums. So the thing is the following. So if you compute Frobenius intertwiner for quantum differential equation associated with Pn, so for Bessel equation, then you can reiterate the Frobenius intertwiner s times. So in total, I mean, the Frobenius intertwiner sends z to the power p, then z to the power p to z to the power p squared, and so on. And last you arrive to z to the power q. And then using this property here, so this product of Frobenius intertwiners is an automorphism of a certain space of solutions. So it makes sense to take its trace. So trace here again over cohomology of Pn. And then the theorem is that this is exactly the Kloosterman sum associated with Q. So Q is p to the power s. And again, this story extends, so exactly the same is true for T star Pn. So if you compute its Frobenius intertwiner, then you get this multiplicative sum, which I mentioned before. So it's a sum over Teichmuller representatives of master functions. So you may think about you may think about trace of Frobenius intertwiner as some kind of a finite field analog of integration. Right? So this whole story becomes motivic. You can integrate, which is evaluation of this motive over complex fields. But if you switch to finite fields, then this motivic integration is replaced by traces of Frobenius intertwiners.
And is there a story which indeed motivic in your which includes quantum differential equations, which indeed sort of different realizations of some motivic story?
Well, I thought this is it, right? So in a sense,
well, it's p-adic, like to replace. Yeah, maybe even the field of p-adic numbers can be replaced by the version of the ring of motivic functions.
Okay, this I don't know.
Yeah. Okay.
Mm-hmm. Well, yeah, and in general, well, one can expect the following thing, right? That if you have X and it's a quantum cohomology, so maybe I write it here. So you have X, you have quantum connection, then you have you construct from Frobenius intertwiners, and then you study its traces as before. And in general, the expectation is that it's going to be sums, as I mentioned before, multiplicative or additive, like here. And the sum is running over some points of certain mirror variety, which I denoted by x check here. So in all examples I considered before, this variety was a torus, but in general it might be more complicated, and it's called a mirror variety, whatever it is, over finite points, finite field points of certain varieties. And I guess in many examples, for example, in the case of Nakajima varieties, I don't know what this thing is, but I think it exists. Yeah. So for instance, I've already mentioned the projective space case. You know, it has well-known superpotential from quantum cohomology, and we get these Kloosterman sums. But you can consider more complicated examples, like for instance, Grassmannian of two-dimensional spaces in a four-dimensional space. Again, from some quantum cohomology literature, we know explicit formulas for superpotentials over this thing. And then J functions are given by the exponents of the integrals of the superpotentials. But the interesting thing is that if you switch to finite sums, so you have four variables here, x1 to x4, and you do not take a sum over torus. So the sum over torus will not give you a trace of Frobenius. It's an interesting thing. So at the beginning, when I computed Frobenius intertwiner for this guy, I computed a trace. I saw that it's going to be like a Kloosterman sum where I need to take this sum with this superpotential over a torus. But it happened to be not correct. And the correct way to do it is to understand that, well, this four-dimensional torus is actually a subtorus, or like a torus chart in some bigger variety. And this bigger variety looks like, again, Grassmannian minus certain canonical divisor. And this variety is known as a precise or like correct mirror for Grassmannian. So it appeared in the work of Marsh-Risch. And there is an interesting story about it. It's a cluster. It's an example of a cluster variety, and so this is like one of the cluster charts in it. But the point is that it's bigger than this four-dimensional torus, and this superpotential extends to a certain well-defined function here. And then if you take a sum,
so in this case, the x check has larger dimension than 4, right?
No. It has the same dimension, but
X check also is a 4 dimension.
It's a four-dimensional, yes, and it's like an open torus in it.
Okay, so that is only a cluster chart. And you said the cluster variety, there's X variety or A variety. Which one?
So I'm saying that this thing is a cluster variety, so it's covered by some kind of by tori, and this is just one of these charts.
Okay.
Yeah. So, but then, yeah. So I decided to try and take a summation over finite field over finite points of this variety with this superpotential, and that's exactly give you again the trace of Frobenius. So in this case, this arithmetic Frobenius detects exactly the known 2D mirror, right? So it's kind of sensitive to that. But there are many more examples in which I don't know what this mirror is. For instance, if you take a cotangent of Grassmannian, it's going to be a Nakajima variety. And again, using the formula I mentioned before, you can compute Frobenius intertwiner or Frobenius automorphism. You can compute its trace. Well, you see that those traces are some interesting integers, but then I don't know how to write this thing as a sum over certain variety. So in this case, I don't know what to X check.
Are you talking about equivariant mirrors or what?
In this case, I have to introduce one equivalent parameter, h bar, which rescales this cotangent direction, again, because it's a non-compact thing.
Okay.
Yeah. Well, I guess that's my story for today. Yeah.
Yeah. Thank you very much. What kind of I'm a bit confused. I mean, it's kind of a general thing. So you want to have to study sort of, for example, arithmetic properties of sums which are similar to Kloosterman sums, but which are related to some more general varieties, or maybe you can say something about classical Kloosterman sums, just using this analogy. So what's your goal? To consider, because you look for more general variety, like instanton or whatever, Coulomb branch, Nakajima. You write, and for example, even if you know the mirror, I don't know, then you write p-adic analog of the integral which appears in this. Okay, good. And so then you can ask the similar questions to whatever people dealing Dwork, actually Dwork asked about Kloosterman sum, but how will you answer them? Do you have any additional tools for that, or you just generalize this? Yeah.
Yeah, there are two questions that I can ask. First of all, as I mentioned already, like if I have a say general Nakajima variety, I can compute its Frobenius intertwiner, I compute its trace, but I don't know in general how to write this trace as a finite sum. Right, so in some simple cases like Kloosterman sum or sum associated with T star, Pn, I get some classical things. In more general situations, I need to enlarge my torus and look at more complicated varieties like these exact mirrors. And in general, I don't know how to construct them for Nakajima varieties. Again, the simplest example in which I don't know what this thing is T star Grassmannian 2-4. So there should be some kind of generalization of this Marsh and Risch construction, but I don't know what it is. So again, one thing which would be nice is to write those traces as some interesting sums. And then another thing would be to write bounds on these sums as before, but these bounds they follow from this explicit formula. So you can from this explicit formula for the gamma class. So as Dwork and Sperber they did it p-adically for Bessel equations. Why they constructed this? Why they consider this Frobenius interpointers? Exactly because from this formula for the gamma class, you can estimate the p-adic valuations of the eigenvalues of the Frobenius intertwiner, and that's exactly what you need to bound. You need to know valuations of eigenvalues to bound your sum, your trace. And so, in a sense, this is kind of on the nose. Since we now know this formula, we know that this traces are bounded by something. But since we don't know how to write this trace as a sum, we don't really know what kind of sum we are trying to bound.
Well, then there is no so far generalization of this p-adic Riemann conjecture for more general.
Yeah.
Okay, well, thank you very much. More questions?
So
okay.
in the geometric setting, and which in terms of mirror symmetry, one works on as a complex variety, but also at the same time, one look at the things over finite fields, and that's where. So, how does the P, relate to this X? For example, in Nakajima quiver variety case, can P divides the dimension vector?
No, it's in a sense. Yeah. So as I said, my understanding is that if you have X, then you can construct this object trace of Frobenius intertwiner, right? And then you want to say that this trace actually computes some sum over X's of something like additive character of something of some superpotential. But then the question is, like in general, from complex mirror symmetry, you know what this S is in many examples, but you need to take a sum over certain variety, which I denote X check, and P appear here as, you take this over finite field points of this variety. Q is some kind of P to the power S.
Yeah.
And so this arithmetic story detects mirror symmetry only in this case, in this sense, that you need to take a finite sum over certain variety.
And as far as I remember, when Hausel was, he didn't do this kind of series, but most of the series he produced was counting the number of rational points over finite field and produce theta functions. But some of the formulas, when the P divides the dimension, that can be a problem. And so I was curious if you have seen any restrictions on the P. So given the X, I can choose any arbitrary P or can. Sometimes one has to exclude a few primes in the formulation.
Maybe it's more like a story when you study these zeta functions of some varieties, but these traces, they are not quite zeta functions of these varieties X or X check. So I don't see any like relations and restrictions on P and dimension of X or X check.
I see. Okay, well, thank you.
More questions? Well, if there are no more questions, thank you, Andrey, and you will continue tomorrow, same time, yeah?
Yeah, thank you.
Okay, thank you. Bye.
Yeah, see you tomorrow. Bye-bye.